to look at thermochemistry, the properties of heat associated with chemical reactions. So we're going to study thermochemistry. This is will give us an intro to thermodynamics. Thermodynamics comes next semester in full force. We're going to study more fully how energy, study the properties of energy and its conversions. Our first law of thermodynamics, conservation of energy. Energy is always conserved. Energy can be converted from one form to another form, but it cannot be created nor destroyed. Energy. Really everything is energy. Even matter is condensed energy. But for our purposes, energy is the capacity to do work or produce heat. We measure energy in terms of the joule, and a joule in base units would be a kilogram times meter squared per second squared. One of our conversion units that we will need to know is between calories and joules. Calories was designed for chemists, joules designed for physicists, but joules was adopted for the SI system, so it's common now, but we still have a lot of calories in our literature. So we need to know that a calorie is 4.184 joules, and this is defined to be exact. So a calorie is 4.184 joules, and this is a thermodynamic calorie. It is not a food calorie. A food calorie is 1,000 thermodynamic calories, or kilocalorie. Kinetic energy is the energy of motion. It depends on its mass and velocity. Kinetic energy is 1/2 mass times velocity squared. For these equations, where we are converting between different properties, we're converting between energy, we're converting between mass, velocity. The simple way to make sure that the units all work out are to use SI units only. If SI units go in, then SI units come out of the equation. So in this case, if our mass is kilograms, velocity is meters per second, that'll give us 1/2 mv squared, gives us units of kilograms meters squared per second squared, which are the base units of joule, so that will then equal joules. The other version of energy is potential energy. Potential energy is energy that is stored or available due to position, such that things high in a gravity well have high potential energy. They can fall in that gravity well, creating kinetic energy. We can also have electric stored in a capacitor, where the strong electric forces hold this potential energy, and then it can be released when the capacitor is discharged. Potential energy can also be stored due to configuration, such as a coiled spring, where the configuration is holding energy, tension energy, against some other force. Or potential energy is also based on composition, chemical energy. And this is one of the ones that we will work with the most, of course. So for composition, if you can find a reaction that will take the reactants to lower energy level, then you can extract energy from that material. We describe our attractive forces in molecules and atoms as electrostatic potential. Electrostatic potential is that opposite charges are attractive, identical charges are repulsive. The electrostatic potential is given by this equation. Electrostatic potential is equal to a constant kappa times Q1, Q2. These are the charges of the particles, and then d is the distance between the two particles. So if we look at the unit here, kappa is 8.99 times 10 to the 9th joules times meter per coulomb squared. So that would mean that our distance would have to be in meters, and our two charges, Q1, Q2, have to be in coulombs to give us joules out for our electrostatic potential. We don't need to memorize this number, but the charge on an electron is negative 1.60 times 10 to the minus 19 coulombs. So when we have the same sign on the two charges, we end up with a positive potential. This is a repulsive potential. When we end up with opposite signs on Q1 and Q2, we end up with a negative potential, and this is an attractive potential. So chemical energy is energy in chemicals that can be released through chemical reactions. One of the more common reactions that we use for extracting chemical energy is just combustion of hydrocarbons to produce carbon dioxide and water. So one of the first law of thermodynamics is the law of conservation of energy. We cannot create or destroy energy. Energy is always conserved. Energy of an isolated system is constant. Energy can be converted from one form to another, but the total energy will always be conserved. Although I have to apologize for the equation here, saying that the energy of the universe is constant by saying the change of energy universe is 0. The universe might not be an isolated system, so the universe may not apply to this equation. But for any isolated system, the energy is always conserved and is constant. But we don't look at the universe usually. We look at a part of the universe. So what we do is we take part of the universe and we examine that part. That part that we examine we call the system. Everything else is the surroundings. So the system is the part that we are working with, that we are studying. Everything else is surroundings. So in our systems, we can define a couple different systems. An isolated system has no exchange of matter or energy with the surroundings. So that would be a theoretically perfect thermos that does not allow any energy exchange. It is perfect thermos does not exist, but we do create some pretty close types of thermoses. A closed system is closed in that there's no exchange of matter. The energy can exchange with the surroundings. This is typical. We can easily make a closed system where we contain all the matter. Energy is always the tough one to contain because energy always flows. And then an open system has an exchange of matter and energy with the surroundings. So a example of that would be a candle flame, where it's always pulling in fresh air and always putting off exhaust gases along with heat and light. So heat is a form of energy. But heat is the energy of random microscopic motion of molecules and atoms. So everything is always moving. All our atoms, all our molecules are always moving. This motion contains energy. And this energy we call heat or temperature. Heat and temperature are two different things. They're two different related things. So heat we would measure in joules, in energy units. Temperature we have other units, Kelvin or Celsius, that we measure temperature in. But temperature and heat are related in that heat only flows spontaneously from high temperature to low temperature. Heat can never flow the other direction. Heat can never spontaneously flow from cool to hot. Heat always flows from hot to cool, from high temperature to low temperature. And when we have a difference of temperatures and heat flow between them, we are able to tap into that heat flow and extract energy out of that heat flow in the form of work. Work is a macroscopic flow, a net flow of energy against a force. So work is a macroscopic flow to push against something. So work is a push against a force over some type of distance. So we could use this work energy to move objects. The force that we are pushing against can be gravity, we can be lifting something. Inertia, we can start motion in something that was still, or stop motion in something that's moving. Or friction, so we can keep something moving even though it's losing energy to friction. Force is mass times acceleration. Work is force times distance. So force has units of kilograms, which is mass, times acceleration, which is meters per second squared. So work done over distance is force done over distance. We multiply the units of force by distance, meters. We end up with kilograms times meters squared per second squared, which is a joule. So that is energy. So heat and work are our two ways of transferring energy. So force is the influence on a body that causes it to accelerate. Or it's a vector equal to the body's time rate of change of momentum.